Good morning. Hello, good morning, everyone. Welcome to the second day of Khipu. We have an amazing day ahead of us. I would like to kick off by thanking our generous sponsors. Without them, this wouldn't be possible, so thank you very much for your support. My name is José Lezama. I'm a professor and researcher here at the Universidad de la República. Today, we will start our day with the second part of the fundamentals lecture on convolutional neural networks. Our next speaker is an outstanding Latin American researcher. He's Juan Carlos Niebles from Stanford University. Juan Carlos received an engineering degree in electronics from Universidad del Norte in Colombia. He received a master's in electrical and computer engineering from the University of Illinois and a Ph.D. in electrical engineering from Princeton. Currently, he is a senior research scientist at the Stanford AI Lab and associate director of research at the Stanford-Toyota Center for AI Research. Not only that, he has also contributed back to the Colombian community. He has been an associate professor of electrical and electronic engineering at Universidad del Norte since 2011. So I could go on with a very large list of impressive achievements, but in the interest of time, I will stop here, and let's give a warm welcome to Juan Carlos.
Wonderful, thank you. Good morning, everyone. It's great to be here. It's my pleasure to come for the first time to Montevideo, and very happy to be here to share with you some of the work we have been doing at Stanford that relates to computer vision. And I'm a computer vision scientist, and that means I build algorithms for understanding images and videos. In particular, I'm very interested in the idea of building systems that can understand what people do and can recognize people's actions and activities. So today I want to talk about the human event understanding, going from actions to tasks. But being a computer vision scientist means that a lot of the work we do is published and shared in some of the academic conferences that happen throughout the world. So I just wanted to share a little bit with you about that in a way to thank the organizers for putting this event together. So I want to thank you by sharing with you some interesting data. So as I said, from computer vision perspective, we have this very good conference, premier conference in the world called CVPR. Some of you may know it. And last time it happened in June in California. And it's interesting what has happened with CVPR. The last few years, we have seen a tremendous growth in the interest. People really want to come to this conference. We had 9,000 people in June attending this conference. So that's amazing. It's really an exciting time to be doing computer vision and AI. And something interesting I saw that day, the organizers were sharing this map indicating where the attendees came from. And it's really striking to see how the numbers are so big for the countries in the Northern Hemisphere, but we still have a long way to go in terms of attendance from our side of the world. So I think there is a big opportunity for us to really get this community together. And the same thing I saw just a couple of weeks ago. I was in Seoul, South Korea, and similar growth. It's really growing so fast, and you can see the interest in these domains are just growing tremendously. So we had 7,000 people in South Korea as the largest ICCV ever. That's the other very top computer vision conference, international conference of computer vision. And if you look at the attendees, the similar thing happened. Again, you can argue that this is farther, it's not in the US, so it's harder for us to go from South America, but attendance wasn't that great from our side of the world. So there's a big opportunity for growth, and I think another example, number of publications per country. This is by looking at the first author affiliation. So I think there's only Brazil there representing South America in that plot. So I think it's a very exciting time. After I saw these plots in ICCV, I shared that it's a very exciting time for computer vision, and we really have a long way to go, but I'm very optimistic for the future. I think events like this, where the community gets together and really encourage everyone to work on these problems that are very interesting and, of course, are of big impact, not only to us in our region, but overall in the world, it's very important. So thank you to organizers. I think this is a great step, and we really need to continue doing this to really get this much better compared to today's state. So that's my way to thank. And if this is true for computer vision, I want to share with you that it may be true for other areas of artificial intelligence. We've had this interesting work coming out of Stanford called the AI Index, which tries to measure the activity in artificial intelligence throughout the world from multiple angles. And some of the interesting angles that we are measuring are activity in academia. So how many people are taking courses in AI, how many papers are being published, and we're again seeing that exponential growth equally in many, many fields of AI. We're also measuring things in industry, how much investment is being done in AI technology, tremendous growth and opportunity there. And we're looking at the national strategies. A lot of governments throughout the world are starting to talk about AI and how this technology will really impact and transform the world. So I think if you're interested in this kind of thing, there's a lot more data in a report we put out every year. So last report we put out in December 2018. So there will be a new one coming out in the near future, and the website is right there. So AIindex.org is one thing, a website you want to look at if this is interesting to you. So that's my way to say thank you. I think this is very important, and we really have to continue doing this and growing the community to improve diversity and participation of Latin America. So with that, I'll now move on to talk about my research work on human event understanding. And I want to start by, again, I said I'm a computer vision scientist, and in computer vision, people always want to say, when we look at images, a single image, we can say so many things about the world, but just by looking at one picture. So we like this saying that an image is worth 1,000 words. And we take these images, for example, and humans can quickly recognize objects, scenes, interactions. And we really want to build algorithms in computer vision that can do the same as humans can. However, in my own research, I'm really interested in going beyond these kind of images and look at how can we develop systems that can really understand video. And one relevant question, of course, is why do we need to go to video? Can't we just do things with images? So I will try to answer that question by looking at these images here. So in reality, these images I took from some videos. They are just frames in video clips. So what I'm going to do is to play those video clips and see if we can, what we can get from those scenes. Okay, so once we see the video, in fact, intentions are revealed. We thought that tiger may be attacking that person, but in reality, the tiger is just being playful. So that's good. And also, we may have thought that that person was packing a suitcase, but in reality, they're unpacking it. So motion can disambiguate things that are just not visible by looking at a single frame. And in fact, if you look at the last example, you actually have to watch for a few more seconds to realize that probably the person doesn't really know the combination lock for that lock. So it's just trying to guess and pick it. So this very high-level intention and goal is very hard to get from a single picture. You have to really see the temporal evolution of things to understand events and high-level intentions and goals. So I think videos are very interesting. It's just the first point I want to make. Videos are really interesting. But they are not only interesting, and they're probably worth a lot more than 1 million words. So, but it's also true that video is very important practically. So if you look at what has happened with video consumption and generation in the last few years, it's just amazing. So millions of hours are watched per day on a movie distribution platform, as well as YouTube, hundreds of hours uploaded to the website every minute. So the amount of video that is coming in is just too hard for everybody to see or anybody to check manually. In fact, Cisco talks about millions of minutes per video crossing the network every second by 2020. And these numbers are already a little old, but still they make the point that video is so important and is being consumed so much by people. There has to be something there. Otherwise, we wouldn't see this much activity. So it's an enormous amount of video being consumed. And of course, my question is, how can we parse and understand all this video automatically? So videos are important practically. And I think one reason why these videos are so important is because humans are the main subject of these videos. And if we think from the human life perspective, events are central to human experience. So everything we think of our life is basically a collection of experiences and events that happen through our life. And people participate in all kinds of events, right? Play with tigers, dance, pack suitcase, and so on. So one of the most important activities that people do is cooking. So let's say you want to watch this cooking show, and you want to learn how to make a new recipe. So what I want you to think about when you're looking at this video is, as you see all the events unfold, I want you to think about them in terms of a temporal scale. So let's say you have this temporal scale that goes from a few seconds to several minutes. So as we see a few seconds of these videos, we as humans perceive actions such as cutting onions or place pasta. So these are very simple, short actions that happen in a few seconds. But as we see more of the video of the event, we perceive that these atomic actions are actually getting combined into more complex actions. Okay, so for example, the complex action of adding the vegetables and the sauce while stirring. And as we see more of the video, then we realize that the sequences of these complex actions actually make up subtasks that the chef is achieving as they are getting towards the final goal. And once we see the entire video, we realize that, okay, so this was a full event of making spaghetti with meatballs. So there's this very interesting compositionality of actions and events that are very intrinsic of actions. And I think that this key observation here that I want to make is that how events seems to be naturally organized in a hierarchy. And there's some kind of partonomy of events going on here. And my question is is this important? Do we need to care about the relation between events from the shorter time scale to the longer time scale? Or we just forget about that and think of them as a flat organization? So my argument is that if we look at literature from psychology, we see that understanding this hierarchical structure for events is very critical for human perception. So for human perception of events, it seems like having this explicit organization of events in a hierarchy is critical for humans to build representations of what's currently happening in the world. So if they really want to understand what's going on, it's very important to have this sense of hierarchy and composition. Second, is key for people to plan their own actions. What you want to do next depends on how your action or your tasks are organized and the relation between them. So planning is, for people's own actions, is very important, having this hierarchy. And there's a lot of interesting research saying that this hierarchy is also very important for remembering and memory. So recalling what has happened in the past really needs this kind of hierarchical structure. So from human perception point of view, it seems like this organization is very important. Now the question is, can we make the case that this is important for computer vision? Do we need to make computer vision systems that have this similar ability to reason about actions and events with a hierarchy? And probably that's true if we want those systems to have capabilities similar to what humans have. But for computer vision, there are a few challenges that we have to address. And one of them is, how do we represent this composition? How can we leverage this compositionality? How do we build models that can really take this into account? And the other one that I think is very important is, how can we deal with the continuity of events? It's very hard to think about very clear boundaries of when a short event happens or when a long event happens and the distinction between them. So both the space of labels as well as the space of how the events are organized seems to be very continuous. So how do we deal with that continuity? Seem to be very interesting challenges. But So one way to deal with the compositionality idea is that, okay, let's say that we start by looking at the shortest time scale. And at this very short time scale, we want to say, let's predefine a set of actions of interest. So remember that at this time scale, we were dealing with things like cutting onions or place pasta, which are very short actions. And so one thing you could do is to say, well, I will just come up with a dictionary of all possible actions that can happen at that atomic scale and build algorithms that can recognize those atomic actions and then go from there to build compositions. So that's one way to do that. And what I'm going to show you now is some of the work we're doing along those lines here. So at this scale of atomic actions, we're trying to study this from the point of view of the temporal action detection problem. So the idea here is that you're given an input video like this, and your goal is now to output the start and ending time of every action of interest. Okay? So here, you may want to say that that first interval corresponds to pole vault and has certain boundaries for when it starts and ends. So that's our goal here. So but of course, this is very challenging because videos have very different length. The duration itself of the action can vary depending on how people perform that. And the number of actions in the video can also change, and so on. So there is a lot of variability that the model needs to deal with. But because this is such a fundamental task in video understanding, there has been a lot of work tackling this problem from different perspectives. So I think I want to organize them in three big categories. So the first category is basically, let's just do some frame-wise classification. So look at every frame independently. So you have frame-level classifiers, which are then sort of post-processed in a completely separate stage that sort of accumulates information through the different frames and does some kind of merging and smoothing to come up with the intervals. So that's one way to do that. Another way, which actually is something that one of my students worked on a few years ago, was let's just, instead of doing this frame by frame, let's come up with a way of proposing interesting intervals within the video. Okay, so you take the video, and instead of considering every possible interval, you come up with a small number of temporal intervals that may contain actions of interest. So that small set of intervals we call proposals. And those temporal proposals are then classified. And the idea here is that because you're only considering a small set of intervals, then the classifier has kind of an easier job to distinguish which ones contain certain actions and which not. So that's another way to do that. And what I'm going to talk about today is kind of a recent family of actions that, or models that try to take a video and directly output the final result by using some kind of deep learning framework that is trained in an end-to-end way. Okay, so that's what I want to talk about now. And in a way, it's very analogous to some of the classical object detection frameworks, except that here we are dealing with the temporal domain rather than the 2D domain in object detection. So the model I want to talk about today is called the SSTAD, or the Single Stream Temporal Action Detection. We presented a couple years ago. And the idea here is that, again, you're taking an input video like that, and we are trying to process the video in a single pass. So the goal here will be every frame I only want to process one time. I don't want to have to reprocess videos multiple times, which may be something you have to do when you're dealing with temporal sliding windows. So here we want to just do a single pass in the similar spirit as in the object detection world, things like YOLO or SSD are doing single shot or single pass detection. So we want to do a temporal version of that looks at every frame only once. And the intuition here is that we want to detect when the action ends. So that's one of the tasks of the model. And the other one is that it will have some kind of memory that remembers when the action had started. Okay, so that's the intuition we want to build into the system. And we want to do that by building this design, which implicitly uses two subtasks. So we're going to design the model in a way that internally it has to solve the two subtasks of localization, so finding where the action is happening in the video. That's one subtask. And the second subtask is to classify that interval into some of the actions of interest we defined at the beginning. All right, so that's what we want to do here. And so the way the model works is, we take an input video. So here we see the arrow of time going down. And given the input video, we divide the video into very short clips. So the short clips here are of size delta, which is roughly 16 frames. And so every 16 frames, we have some kind of short clip. So we take that short clip and pass it through a convolutional neural network that is used to extract features. Okay, so these are the typical convolutional neural networks for video, which at the time we built the system, the most popular one was called C3D, which is basically similar to the convolutional neural networks we saw yesterday, but they handle time by adding this another dimension to do three-dimensional convolutions with the video volume instead of the single frames. So it's just an extended version of the 2D CNNs for video. So that's what we do. We take the 16-frame clip, pass it through the visual encoder, again, which is a video feature structure based on convolutional neural nets. And then we have our memory modules, which really are going to do the job of remembering and detecting and dealing with the temporal signal. Okay, so for that time step, we have the information passing through to these two memory modules, which will accumulate context for these two subtasks. So one module is doing the localization job. That's the P green module at the top. And we have the other classification module in blue, which is classifying what the single clip is doing. So these are sort of the two subtasks. And then we take those intermediate results and have an additional layer that directly outputs the intervals of interest. So here at the end, we have, let's say, we're considering this temporal clip delta. So we're only dealing with all the intervals that end at this time. So that's why the ending is sort of aligned here. And for all the intervals that end here, we also consider all the potential initial positions for the intervals themselves. So we have very short intervals that end here, but also very long intervals that end here. And for every interval we're considering there, we classify it to one of the potential actions. Okay, so that's kind of the output we're going to get there. Different interval sizes and different categories. So we have these class scores directly over this multiple scale temporal grid. So that's what the end-to-end system is, how the end-to-end system is built. And I think one of the interesting things we did here, I mean, this seems like a reasonable design for the architecture, but one of the interesting things we saw here is that we built this idea of semantic constraints to train the system. So I'm going to try to explain what that means. So the idea of semantic constraints is, well, we have this end task, which is detection. We represent by this figure here. And we have these two subtasks, which are localization and classification. So the way you would typically train the system is to have this loss function that is composed by three components. One is dealing with the end task, and the other two dealing with the intermediate subtasks. So here we have the three loss functions, or accumulation of the three loss functions, one dealing with the detection, classification, and final result. So the typical way of training this would be to use a multitask approach, which means I come up with some kind of weighting of the three losses. So I have some weight or some importance for the first, second, and third loss. And we set them to some constant and then train the system jointly. Okay, so that's the typical multitask training. What we wanted to do with the semantic constraints was to think of them as training wheels, or thinking of the subtasks as a way to provide some guidance to the system, especially at the beginning of training, where the model could potentially focus more on the easier tasks first and then deal with the harder tasks later. So instead of thinking of learning everything at the same rate, we came up with this. It's kind of like a curriculum learning scheme based on tasks. So it's a task curriculum scheme, where at the beginning of training, we give a lot more importance to the easier subtasks. So these tasks that are dealing with the two submodules seem easier for the model to learn. And then as training progresses through time, we reduce the importance of those easier tasks and then focus on the harder tasks at the end. And again, the idea is to have some kind of task curriculum where we give training wheels to the system by letting it focus on the easier tasks first and then focus on the harder tasks later. And the advantage of this is that you get faster training, so you get your model to train quicker, but also you get higher end performance, which was very interesting. And the way to try to show that is that if you had no semantic constraints, you had no subtasks, so this is what training would look like only for dealing with the one loss function at the end. If you were to do multitask training, which means you add these extra losses with fixed importance, fixed lambda, then you get this improved speed in training, but you get roughly the same performance. But when we tried this idea of dynamically changing the importance of the tasks, we saw that the model actually trains as quick as the multitask setting, but ends up at a much better optimization point. So that was very interesting. And we're not sure how much this generalizes to other settings, but it seems to be very useful for our case. So of course, we had to show that at the end of the day, the system somehow improves the existing techniques, and at the time, we achieved state-of-the-art performances in one of the typical benchmarks for action classification called Thumos 14. But the cool thing about that is that our model was very fast because we had this design philosophy of looking at every frame only once. We were able to really run this very quickly. We had over 700 frames per second on a typical GPU of the time. So that was great. And, but I want to update those numbers a little bit by saying that, in fact, we came back to revisit those visual encoders. And again, remember that that's the part where the convolutional neural network is sort of extracting the features. And we said, OK, let's see what's the most recent developments on this. And we found that instead of dealing with the three-dimensional convolution as a single block, there were some newer architectures that were decoupling the space and temporal components to achieve much better performance in feature extraction. So all we did was to replace this component by a newer convolutional neural network and then retrain the entire system again. By doing that, we actually found that a couple of years later, we now again outperform all the existing methods, even methods that not only, so in our setting, we only use the color information from the video, but another thing you could do is to use optical flow to augment your features. So here we're comparing to other systems that use not only color, but also optical flow, and we see that even though we don't need the optical flow computation, which is very expensive, we can still obtain state-of-the-art performances. So that's great. And let me show you now some results. So here we have examples in basketball. And basketball, I think we're looking for the basketball dunk action. So you can see there that the video sort of speeds up through the parts where no actions of interest are happening, and then slows down to show you where it has detected the basketball dunk. The same thing for the pool example, where we're trying to find diving into a pool. And again, this is a very long video where there's a lot of stuff happening, but the model is able to quickly parse through all the boring parts and really focus on the segments where the actions happen. So there are example results, and some more examples where we have multiple viewpoints. So here, I think it's the throw and frisbee throw we're trying to detect, and frisbee catch. And also in the baseball case, we're trying to find pitching. And even though there is some slow motion and so on, the model seems to be quite robust to that. And here's an example of different action classes. So we have cricket throw and cricket hit and cricket shot. I don't remember the exact naming of cricket, but again, the model also handles the multiple action case very well. All right. So that's what we can do when we're dealing with atomic actions. We have these short actions that we can predefine. We can come up with a vocabulary of actions. In many domains, that's possible. Like sports, you can come up with a few set of actions that you want to detect, and then you can train a system in a supervised way, as I just showed you. So that's great, but it does have some limitations. I'm not totally convinced that we can simply discretize all actions into classes. And it may be true for some specific applications domains, as I mentioned in sports, but when we think of general human actions and behavior, it seems very hard to come up with a definite set of actions that would be general to all possible human behavior. So I'm just not convinced that we can discretize actions to a fixed set of tokens. So what can we do there? So one idea would be that, well, as you go up in this complexity scale or this temporal scale, perhaps you can use language to drive the model to know what to recognize. So here we're dealing with these complex actions that can be described with these longer sentences. And even in this case, it's not clear that we can simply guarantee that we have access to all the possible units, right? So perhaps what we can do is to embrace the compositionality of language itself. Language, especially when talking about actions, really needs to construct these complex sentences to be able to convey what the actions are. So perhaps we can just embrace that compositionality that is coming from language and work with that. How are we doing with time? So how much more will we have? 20 more minutes, great. So the idea here will then to study this problem of dealing with complex actions, and we study it from the point of view of retrieval of complex actions. So here's the problem I want to study. So given an input query like this, so there's a sentence that I want to recognize or find in a video. I'm also given that video, and the task would be to locate that query within the video. So let's say that given that sentence, I want to know where the sentence happens in the video, or the action described by the sentence happens in the video. And see that this is very different to the setting we had before. Before, we had a predefined set of categories. Here, I just don't know what the sentence is going to be. It can be anything. So it's a very different setting. So, and what we are thinking is that perhaps composite events can be broken down into simpler events just by looking at the way the event is described. So given an input, a query sentence like this, we can think of it as a composition of a girl that is riding a bike and then a girl that is falling. So we have these two different things that happen, and they get composed, right? So one idea is, well, perhaps we can use language to drive those compositions for the model. So then language can drive two things. One is what to look for. So the sentence itself will be describing what's the action that we need to look for or need to locate. And the second thing is where to look for that event. So there are two things that the language can tell me: what to look for and where to look for it. In a way, the where is about the structure of the event itself. What happens first, what happens afterwards. So we said, okay, what's the simplest thing we can do with this? Well, let's say we have this sentence, and what we can do is to run it through, we have a video as well. So what we can do is to run that sentence through a parsing algorithm to get a parse tree, okay? And so that parse tree will tell me the structure of the sentence. And what I can do is to say, well, let's use that structure directly to build the structure for our neural network. Okay, so that's exactly what we're going to do here. And I'm not going to claim that this is the most optimal way, but it's just the simplest thing we could come up with. So run the sentence through a parser, get the structure, and then use that exact same structure to come up with some modules and the arrangement of modules in the same way. So, but then there's one more thing I have to do, which is how each module is parameterized. What is each module looking for? And I can do that again by parameterizing those modules with the language. So let's say that this module over here, when it's trying to do the processing of the video, it has to be looking for the word bike or byte. So that's the idea, that the language would parameterize the module itself to come up with what to look for within the video. So now, given the structure and the parameters, I can now evaluate how well this video or sentence matches to the video, and I can come up with a correspondence score that tells me whether these two things match or not. And we have some evaluation, but I'm just going to skip this for now to show you more intuitions of how this is working. So we come up with this sentence, and we have the tree for the sentence. So every word will parameterize some module, and the module will tell me where that word happens within the video. And I accumulate, using the tree information, I can accumulate these words to say, well, now this is birds and window, and it has not only the information of that sentence embedded here, but also information of the sibling nodes. And they accumulate and aggregate. And I can keep aggregating to come up with the final sentence at the end. Okay, so the aggregation happens in the order that the parsing tree has given to me, and then the parameters are given by the words themselves. So at the end of the day, I end up with a confidence score that tells me how well that sentence matches every component or every temporal interval within the video. And the final result that I can get is something like this, where I'm looking for a baby putting their hand in their mouth while laughing, and you can see that the confidence score goes higher exactly when the action is occurring. There you go. And here are more examples where we see a horse ice skating, if that can happen, well, it's there. And then the door is open and two dogs running outside. And again, the confidence seems to match exactly when the action happens. Here's a girl climbing ladder, and so on. Okay, so, and again, I think there are things here that we didn't have enough time to explore, but clearly you could improve this by doing a better job in coming up with a structure for the model. I think we did see that the sentence, the parsing tree from the sentence can be fragile, and there's a lot of room for improvement there. So introducing some learning of the structure would be interesting there. So that's what we have been doing for complex actions, and it's an example of how we can use language to drive visual models to recognize things in videos. But of course, the limitations, clearly, if my language description is too simple, then there's nothing I can do with this. Or if my language description is too long and complex, again, the model will have trouble there. So there are some clear limitations, and sometimes I don't really want to get the structure of the event from the language, but I may want to get the structure of the event from the video itself. So that may be another thing I want to do, not using the language itself for the structure, but looking at the video and coming up with the structure from the video. And that's very important, in particular, as we go up to these longer-term events, like tasks and subtasks, where, as we move up in this temporal scale, we see that here, understanding and extracting the event structure is a lot more important. It's really to understand what's going on. It's key to know what may be happening. So at this scale, I think one important goal for a model is to really try to understand and extract event structure from the video. So we did some study of this, and the idea was to go from video to structures. So we're going to assume that we're given a few videos, or not a few, but a good number of videos that have this kind of decomposition. So the video itself is divided into a step-by-step linear timeline, where at every step in time, we have some kind of description of what's going on during that time step. Okay, so we have a video that is divided into sort of a sequence of segments, and every segment is described somehow. And this is typically easily obtainable from instructional videos, where the structure is sort of explaining what's going on at every time step. So that's the starting point for us. And what we want to do is to go from here, the sort of linear step-by-step timeline, into a graph, a structure that has grounding for the objects that are being manipulated, and also has some understanding of dependency between events. So that's what I want. Come up with a task structure in a very nice graph representation. Okay, so let's see what we have done here. So, so let's say we're watching this video of somebody making a Caesar salad, and as we see the video, the structure may say something like, now take the green mixture. And we know that they're referring to one specific bowl in the scene. We know they're talking about this particular object here. So for us, it's very easy to do this association. We associate what they say with the objects in the scene. But for computer vision systems, this is what we call visual grounding, where you take some entity in text and you try to locate it in the frame. Okay, so that's one of the things we need to do. And that's what we want to do now. But the problem is that sometimes this structure is not very explicit. They may say, instead of taking the green mixture, they may say, now take it. Okay, now how do I build an it detector? I cannot just simply go to ImageNet and find it and build a classifier for that. There's something else I have to do. And, but even sometimes the structure would completely omit the pronoun. Now, even worse, okay? But our goal is still going to be to ground all these cases. We want to come up with a way of finding them in the video. So how do we do that? The key is that without the context of the task, this visual grounding would be very difficult to resolve. So you have to really take into account what's going on in the entire sequence of events in your task. And that's the keyword we want to use here. So unless we know this context, it's very difficult to know what it refers to. And the solution is that to really find it, what we need to do is to take this in context into account. And in this case, what that means is go back to the previous steps and see what the structure had said. Maybe they have said something like, mix the salad greens just beforehand, and then they said, now take it. So if we can resolve what they are referring to by looking at the previous steps, we probably can have the context required to ground these very difficult pronouns. Let me see, let's skip something. Okay, so two objectives here. The first objective is going to be to jointly resolve the context references. So those are the green arrows. We want to know what each entity is being referred to in the previous steps. So that's the first thing. And we want to use it for grounding. Okay? But the problem is that you can imagine that doing this in a typically supervised way, as many of the deep learning systems today are, would be very difficult, because we would need to have this full graph annotation over many, many instructional videos, and that may be really expensive to get. So we don't want to annotate this. We want to also train this without any explicit grounding supervision. So that means we don't want to use any labels for the references or any labels for the grounding during training time. So that's going to be challenging. But putting these two things together, we came up with a system that we call the weakly supervised and reference-aware visual grounding. And I'm going to try to talk to you about how it works, at least at the high level. OK, so we can think of our problem in terms of a graph. So the idea here is that we have input nodes, and the input nodes are actions. So let's say what the step is doing. Remember that we had this sequence of steps, and every step had some description. So the nodes are the actions that are happening, or the descriptions that are happening at every time step. And then we have entities. Those entities are the ones that we need to ground into the image. And we can get them through parsing. So again, we have the speech of the structure. We have some other source in which we can parse and come up with the entity. So we can get that somewhat automatically. And the other input for our system are going to be these bounding box proposals. Again, proposals are a subset of windows that may be interesting within the frame. And so we have a few set of proposals or a small set of proposals from each frame, and we can obtain that from, again, a neural network that does region proposals from single images. So we can get that, again, using a pre-trained system from the state of the art. And then, so the output of what we want to do are edges. So that's the output of our algorithm. two edges. One is the reference, again, the green arrow that tells me what it refers to in the previous steps. So that would match entities to actions. And the other one would be the grounding of entities to boxes. So we have the blue arrows that tell me what each entity is referring to within the frame. Those are the two outputs we want to get. So the way we solve this is by doing this dual optimization process where we need to resolve for these two things. So if you can imagine that if you know what the references were, then it's easy for you to locate to do the grounding because you know what it is referring to. But at the same time, if you know the grounding, you know that it is that bowl, then it's easy to solve the reference. So what we do is to alternate between these two things and try to come up with a solution of the optimization. I think I don't have time to go over the details of how any of this work, but what I'm going to do is to just jump over to some of the results that we can get with this type of approach. So here, again, we're putting all this together by starting with our timeline of actions that we want to process. So this is the making spaghetti and meatball task. And we have this temporal timeline of segments. Each of them tell me what's going on. And this is the output of our visually grounded action graph. So we have the sequence of all steps with, actually the colors are inverted here. So green arrows grounding the entities and blue arrows doing the references. So let me zoom in a little bit to try to show you what's going on here. So if you take a closer look, we can see that our model is actually able to provide grounding and reference edges for different subtasks in the overall cooking task here. So for instance, we have the onion here that is it has a reference to null because nothing had happened before, but it is grounded correctly to the first frame here. So the onions are chopped there. And bowl, again, has no reference because it's just the first step. So, but the bowl is detected correctly here. The ground beef is detected correctly here. So again, this is done without any pre-training on any of these objects. It's just by looking at the context and having some knowledge of the objects. And we see that the same thing happens as we go through the entire action. So at the beginning, we see the person making the meatballs, then cooking and preparing the sauce and so on. So we get this kind of nice sequence of actions and the relation between them. Okay? So here's more example of, again, the relations that we extract together with the groundings of different objects, the spaghetti, water, sauce, and so on. Great. So I think this is really exciting. I think this is a graph is potentially a path towards coming up with this, I was mentioning this grounded dependency structure. I don't think I can claim yet that this is really dependencies in the causal sense. I think this is really language relations, but I think it's a step towards thinking about the causal relations and what goes after, what goes before, and why in a very complex task like this. So hopefully this will be interesting in the future. I think there are two particular applications that I find this interesting for. If we are able to build algorithms that understand tasks, understand people's goals, we can build, for example, virtual coaches that can help train people. So if you are learning how to cook this new recipe, you could get automatic feedback on what parts to improve and so on. So to do that, really it's important to understand the structure of tasks. And the other thing that I feel is really interesting, which again, I won't have enough time to tell you about today, but it's about the robotic learning from demonstrations. So if you were able to show a robot how to accomplish a task just by demonstrating it as what the instructional video is like, then it would be really nice to have a scalable learning for robots, especially for home robots. That seem to be an interesting future application. So that's kind of what I wanted to share with you. Looking back at this partonomy of events, I think there is clearly a lot to do. I mean, we're just scratching the surface here, and there's a lot to be explored and multiple open questions. For example, to me, these are all very interesting. How many levels do we need to define in this hierarchy? I kind of came up with 3 and told you examples about those 3, but it's not very clear that this is easily definable. But I think it's worth thinking about it. How many levels do we want in this partonomy? And how do we come up with discrete units? What are the parts that we need to detect? How do we deal with the composition of those parts? And what can that enable? I think if you really can do this composition analysis, I hope that system would be easier to train with less data because they can generalize better from just a few examples by having the semantic knowledge of the compositions and units and so on. So I think that's an interesting question. And again, I think language will play a big role here in some way. I think understanding when we can drive recognition from language, when we have to go do the other way around, use recognition to drive language, I think are interesting questions. So I think that's all I had for today. I think we have enough time for questions, and thank you for coming today.
Okay, we have time for a few questions.
Yeah. Could you here?
Okay, here.
Could you comment on the amount of compute to run some of the experiments and the models?
Great, thanks. Great question. We struggle a lot with having enough compute to do much of the research. But we care about efficiency. I think here I was mentioning that we are able to run these models at inference time with a very fast speed. But it turns out that the training, for instance, in this type of approach, it's really only happening at the higher layers. What we do is that we rely on pre-trained feature structures and then build on top of that. I found that's a way of trying to do research in academia that doesn't need to compete with the big companies doing architecture search and all kinds of things that we cannot do in academia. So I think you can rely on them doing that kind of job and build on top of that is what we have found to be scalable for our case. So yeah, I don't think that we have infinite compute. I think all of these need to be thought of and designed in a way that they are runnable on a couple of GPUs. And that's roughly the scale that I would say we tend to use for this. I think there was a question here.
You believe that computer vision now is superior to human vision, or maybe the question is, does computer vision need inspirations from human visions?
Yeah, great question. I think, do we need to look at human vision to build computer vision systems? Well, I think at the beginning of my talk, I was trying to argue that some of the capabilities for human perception are very interesting and seem way out and still far to be achievable by computers. And I do think that doing vision that is inspired by human vision, at the end of the day, the human visual system is the best vision system we know of. And I think the only issue is, a lot of people make this parallel with airplanes. I'm sure you have seen it, where we build airplanes not by doing exactly what birds do, because that's not as efficient. So, we are inspired by it, but it doesn't mean we have to replicate. I don't think we have to replicate a brain to be able to do vision, but we can be inspired by the capabilities of human vision to build vision system, and that's kind of what I was arguing in part of the hierarchy and the partonomy. So that's my view on that. There were questions here.
Hi. So I was wondering whether once you already know a sequence, you could use this system as in a supervisional mode, meaning that once you know the sequence of tasks, could you have a system monitoring whether when a person or robot is doing it? And how easily would it be to get confused when it skips a step or if it does things in a different order?
Great question. So yeah, that's exactly what I was trying to point out when I said we can hopefully in the future build virtual coaches. And what I was thinking is that if the model has been trained and understand different tasks, then having this knowledge can be useful to give feedback. I think there are a few angles to think about this. I think things like knowing that a step was skipped is easier, but knowing if you are doing the mixture well or not is harder. But I think there is an avenue there for skill assessment and deep motor skills, or maybe for sports, you think of diving or figure skating, things where you can analyze motion and determine skill. That can also be applied here if you were to go to that low level of detail saying, okay, you have to improve how you're mixing your sauce instead of you forgot to mix the sauce. So I think there are different levels in which this could be used. But right now, we're really focusing on the high-level task structure rather than the actual details of each step. Does that make sense? Yeah.
Hi, Juan Carlos. Thank you for the nice talk. So my question is that usually when one watch a video, usually because of the sequential nature of the video, you are kind of predicting what is next. So that is kind of, you are kind of guessing the future. And it's related maybe to the last question. So to me, that is saying that you are using some kind of top-down feedback, some reasoning, and you are using top-down feedback. So in the models that you just show us, most of the processing is mostly bottom-up. So my question is that if you are maybe doing some research or you think it's important to also add to this model this top-down feedback, or maybe we can just understand the videos using just bottom-up process.
Yeah, that's a great question. Thank you, Alvaro. I think there are several things. One is, yes, prediction is important. I think anticipation is key. And I think that's an area in which I've been doing some work. I didn't show any of that today, but I think having systems that can anticipate the future is very important. I think that is clearly important for robotics, for self-driving cars, and other applications. So I think that is true. We have to be able to anticipate at multiple levels of abstraction. We have to be able to anticipate trajectories of people, how they walk. We want to anticipate actions. Are they going to cross the street or not? We might want to anticipate high-level behaviors. So I think at different levels of abstraction, you may want to have some anticipation capability. Now, the interplay between top-down and bottom-up, I think perhaps I can answer that this way. I think right now, the way we're building is, yes, from the observation of the video, we're trying to come up with a structure. We don't have access to a written recipe. So perhaps if you had access to a written recipe beforehand, we could use that as information of, in conjunction with the video itself to come up with a better structure that tells you how steps are organized or so on. So yes, I think there is a role for prior knowledge to be used. But as you know, we have been doing some work together as well on trying to incorporate this kind of prior knowledge, which is it's not trivial, it's hard to do, but I think it's something that we have to be exploring more. Great.
So what I was going to ask you is, the way we humans describe video changes from person to person. We might use different nouns, and we might say things in different order, and the order in which we say things might not correspond to the order in which they appear in the video. So when you're doing the second part of your talk, that you use language first, and then you try to search for the different words, how does that change depending on different descriptions?
Yeah, that's a great question. I agree. That's as I said, right now, the way that model works is that we take the sentence, we get a parse tree, and then use the tree to structure our model. It doesn't, so the way, let me just show you one visualization. So I think as you can see, we have this kind of attentions over the video. We have scores that tell over the sequence of frames that are below each module. And I think right now, even though the words may imply some order, it's not strictly followed by the model. So it can still find things at the beginning or end, depending on the language itself, but also uses, of course, the sentence. So yeah, I think the order that is given in the sentence is, it's not always used directly. So that may give it some robustness to the different ways in which you talk about one event. But clearly, as I said during my talk, is that I still feel like this structure is not optimal. This clearly is suboptimal, and I think there is some opportunity to try to incorporate things like various ways of saying the same thing to find a given structure.
Okay, I'm going to use the remaining time to take one question from the virtual audience. First, let me remind everyone that we have this web app where people can post questions and upvote them. The link is in the program. So the question is, when you cut videos into short clips, how do you make sure that you're not cutting into the middle of some action? So how do you choose when to cut and how much to cut?
Yeah, that's a good question. In a way, our models sort of have an understanding of those short actions, and so through looking at multiple examples, the models get a sense of how an action starts and how an action ends. So in a way, the model sort of expects to see, for example, if it's a long jump, it would expect to see first the person running, then the person jumping, then the person walking away. So by looking at many examples, it sort of builds this internal structure knowledge of what the action is expected to be like. And then it learns to detect the boundaries. But there's no explicit, in that particular action detection component, there is no explicit knowledge of the structure. And I feel like that's something very important to obtain very high robustness to the kind of things the question is asking about. So that's why in the later part I was arguing about this structure as one important cue. And so yeah, I think that's one way to think about that.
Okay, thank you very much. Let's thank our speaker.
Thank you.